Okay. Then when we proceed, then you can now see, I realized, were people getting me or I was talking to myself? I've realized I'd muted my mic. Did people get anything? Those who are in, can you talk to me? Just fat. Were you getting me ama nilikuwa najiongelesha? Because I've realized the mic was muted.
Yeah.
Amjasikia kitu.
Yeah.
Hi, and I've been talking. So let me start because I've realized the mic was muted. So I'll start again. I started by saying that last week we were talking about the authorities that are involved in a power system. So mute your mics now. I'm the only one who's supposed to unmute. You just click on the mic and it will mute. Okay. Now, last week, you remember we talked about the authorities that are involved in a power system, that is generation, distribution, and even transmission. We say the bodies that are involved in the transmission of power are bodies like the Kenya transmission network, that is the KETRACO. Then we have some generation like now the KenGen. We have the GDC, which use geothermal to generate power. We had things like nuclear, the Kenya Nuclear Authority. We had so many of them. So from the general perspective, so today we are going to talk about now the power system. What is the system, or what does the power distribution involve? So from a general perspective, an electric power system is usually understood as a very large network that links power plants, large or small, to loads by means of electric grid that may span a whole continent, such as Europe or even Africa. All these continents, they have huge power systems. Like now, our country, Kenya, we have a huge power system, starting right the way from KenGen, where generation happens, to the distribution, where KETRACO comes in and distributes power, and then to the consumption, where now Kenya Power comes in and distribute this power to the consumers, and we are able to consume and get use the power or the electricity in our houses. The structure now, you can see now the structure on the picture, you can see the picture there. This structure, the structure on the picture is of a plant, a generation plant. Now the power system thus typically extends from the power plant right up to the socket inside consumers' premises. These are sometimes referred to as power systems, as they are autonomous. So small power systems could be made a part of sections or a larger full scheme. You can see. Now we also have subsystems that are in the power system. Now, like now, the distributed generation and even the independent generators, they have different power subsystems. Now, this is the electric generator connected to the grid, the power grid. This is how power is connected. After power is supplied, now the supply network, you can see this is just a schematic diagram, just a sketch to show what happens. Now when power is supplied, it goes through a breaker before it goes through a motor and then the final load. That is the electric motor connected to the power grid. That it means that now it is consuming power. But now when the same motor is acting as a generator, now it is a turbine. It acts like a turbine and then it's connected to electric generator. And then there's a breaker. Now this is the breaker that is connecting to the grid. And this is now the supply network. So in this case, the generator is supplying power to the system. And in the first case, the motor is withdrawing power from the system. And we talked about, when we were talking about electrical machines, we said that electrical machines can either be generators or motors. They can either be used as generators or motors. So this is a typical schematic diagram of what happens when it is connected to the grid. So when it is tapping from the grid, it becomes now, it gives power to the load. But when it is supplying to the grid, it becomes the supply to the network. Now the power system that are of interest for the purpose of the large-scale full power system that span large distances and have been deployed over decades by power companies. Generation is the production of electricity at power stations and generating units where a form of primary energy is converted into electricity. Transmission is the network that moves power from one part of a country or a region to another. It is usually a well-interconnected infrastructure in which multiple power lines link different stations. So with change voltage levels, offering enhanced redundancy, distribution finally delivers the power. Now we could say locally when compared to the transmission system. Also, the final loads, that is in bracket, the majority of which are supplied at low voltage via the intermediate steps at which the voltage is converted down, transformed to lower levels. So the distribution system ends up at the energy consumption point or loads where power is used for its final purpose. There are parts of the world in which the deregulation and privatization of the industry has already completely changed and the industry landscape, while in others the impact is still seen. That's the systems that are involved in power. So now we come to power generation. What happens in power generation? Very big machines are used, that is alternators. They are very big alternators that are coupled together. You can now see now the power plants convert the energy stored in the fuel, that is mainly coal, oil, natural gas, enriched uranium, or renewable energies, water, wind, solar, into electric energy. All these are the stored energy. And you remember, the principle in electrical energy is we cannot store that electrical energy. So the moment it is produced, it's normally used. It is produced at the same time it is being utilized. So the conventional modern generators produce electricity at a frequency that is multiple of the rotation speed of the machine. So voltage is usually no more than 6 to 14 kilovolts. The power output is determined by the amount of steam driving the turbine, which depends mainly on the boiler voltage of that power and determined by the current in rotating. Ready for that? We proceed now. Now you can now see now the transmission. We have already done the generation. Now we are going to the next step of transmission. After power is generated at the generating station, it is transmitted. Transmission is just transportation. We cannot transport power in tanks like the way we transport oil or other petroleum products. Power is normally transmitted in power lines. So now transmission system, the power from the generation plants is carried first through the transmission system, which consists of the transmission line that carry electric power at different voltage levels. So transmission system corresponds to a network meshed topology infrastructure connecting generation and substations together with a grid that usually is defined at 100 kilovolts or more. So when we look at this diagram, my diagram down here, it is a transmission system. The color codes are given so that it can be able to show where we are at which step. The red is the generation. Now at this point, power is generated. Blue is the transmission. It is transmitted to a power station that is far away, that it's called substations. So then the green is now the distribution. You can see now it's distributed to different power stations. Transmission meaning it is going the way it is. That is at 130, 33 volt, at 32. It's normally 132 or 240 kilovolts. You can see that. That is the generator step-up transformer. At the generating station, when power has already been generated, it is stepped up. It is stepped up to 132 kilovolts so that it can be able to be transmitted. So the moment it is transmitted, it reaches at this point, and then it meets the step-down transformer. So this step-down transformer, and at this point, we have a step down transformer. The step down now steps it down to either 33 kilovolts, to any kilovolts that is needed. Now we have now the sub transmission customer there, the primary customer, and then the secondary customers there. Now the primary customers are people like now those ones that are going to transmit now, like the Kenya Power. The Kenya Power takes in first, and then it's able to distribute it to the secondary customers, which are people like industries and us. So the electric power system is there. Electricity flow over high voltage, that is HV transmission lines, to a series of substations where the voltage is stepped down by transformers as levels appropriate for the distribution system. So the alternating current root mean square voltage levels. Preferred root mean square levels are internationally standardized for the power. Okay. So you can see now that the voltages and the ratings, where the transmission takes in place. We normally have the 66 kilovolts, the 33 kilovolts. The 132, we said it's the transmission kilovolts. So in case the systems are having a normal voltage between 100 and 1000 inclusive, that is standard for 3-phase and 4-wire system, that is at 50 frequency hertz or 60. And normally the standard frequency for our country, Kenya, is 50 hertz, and also 120 to that for 60. Now for a 3-wire system, 340 between the phase is standard for the 50 hertz, which is the 240 voltages, which we normally use, and for 60 hertz for the single phase, a 3-phase wire system. So that those are the standards of transmission that are normally internationally set. The middle voltage, that is the MV, is a concept that is used in some countries, e.g. the United Kingdom and Australia. That it is any set of voltage level lying between the low, high voltage and problem. And the problem to define is that the actual boundary between the MV and the HV levels depends on the local practices. So distribution systems, now we have already done the transmission. Now we are on distribution systems. Distribution system is widely recognized in the most challenging part of the small grid due to its ambiguity. Now the voltage levels of 132 is of usual HV levels can be found in the distribution network. The voltage between 30, 40, 10 kilovolts are commonly found in the MV networks, which is not very common in our country. Now, distribution levels of 1 kilovolts are within what is known as the low voltage. The low voltage is what now we normally use or we normally absorb or mostly have in our country, which is normally as the 11 kV. We normally call it 11 kV. Now, the topologies, the topologies of distribution topologies of the system distribution. I was trying to save the attendance users. Okay, it's already done. And then now we have different topologies. We have the radio topology. Radio lines are used to connect primary substations, that is PS, with the secondary substations, and the secondary substations among them. Now the MV lines, that is the feeder, will be used exclusively for one substation or can be used to reach several of them. Okay, the radial systems keep central control of. Caroline, I'm trying to mute you. You will get me. Just mute. I'm trying to mute you and you are unmuting. Radial systems keep central control and all the substations. So we can now see the radial feeder system, the way it looks like. Now this circuit breaker comes from the main, that is the main distribution or the transmission line, to now the zone substation to that is the one for the 11 kilovolts or the 6.6 kV bus. So you can see now the radial means one, all of them are tapping radially from the main feeder, and these circuit breakers are going to fill other substations. So the radial feeder system is now there. What about the ring topology? In the ring topology, it's a fault tolerant topology to overcome the weakness of the radial topology. When there is a disconnection of one element of the MV line, now that interrupts electricity service or service outage in the rest of the connected substation. So a ring topology is an improved evaluation of the radial topology, connecting substations to other MV lines to create redundancy. Independency of the physical configuration, the grid is operated radially, but on the event of failure in a feeder. So other elements are maneuvered to configure the grid in such a way that the outages are avoided. So ring topology is one of the solutions. We realize that this kind of topology, which is the radial, once one circuit breaker, maybe one gets affected like this, it will have to cut the supply for the rest of the subsequent feeders. So which has a shortfalling. So the ring topology comes in to solve that problem for the radial topology. So you can now see how the ring happens. It means that each breaker, these are the breakers, they are tapping it from the main. You can see now this is a transformer supplying, and this is another one, and this is another one. So this one is independent of this, and they are parallel to each other. So the arrangement, now you can see that is the ring bus. The network topology. Network topology consists of the primary and secondary substations connected through multiple MVs lines to provide a variety of distribution alternatives. Thus, the configuration options to overcome failures are multiple, and in the event of failure, alternative solutions may be found to reroute electricity. So you can now see the LV distribution system can be a single phase or three phase. For example, they are usually three phase, 340 or 330 or 400 systems. Now you can now see those. Now the LV grid represents more complex and heterogeneous topologies. That MV grids, that is the exact topology of the LV systems, depend on the extension and specific features of the service area. The type, number, and density of the point supply loads, country-specific and utility-specific operating procedures, and the range of the options and the standards. So those are the topologies that we have. You can now see now these are now the network topology is there. Now we have the generator, a generator, and then the loads. They tap in power, they balance the power output, and they balance the loads. So the distribution system, as now we have the network, a distribution system. This is a secondary substation typically supplies electricity to one or several lines with one of the multiple MV or MV transformers at the same site. So the LV topology is typically radial, having multiple branches that connect to extended feeders. But there are also cases of networked grids and even ring and or dual fed configuration in L networks. So the LV lines are typically shorter than MV lines. The LV, I said they are the low voltage, and their characteristics are different depending on their surface area. So those are the systems that we have, the supply systems that we have. Now we are going to the next slide, which is the primary and the secondary. Primary and secondary power distribution system layout, and which are explained. Now we have the primary systems. You can see now these are panels or the control panels that are used to control power generation. And I remember telling you that when we were back at the university, we visited the Iber Africa, and most of you came into contact with such panels. So how do the panels work? Let me save again the names. So the primary and secondary power distribution systems and layout. Now we have the primary distribution system. The primary distribution system consists of feeders that deliver power from distribution substation to distribution transformers. A feeder usually begins with a feeder breaker at the distribution substation. Many feeders leave substation in a concrete dust and are routed by a nearby pole. You can now see now the primary and secondary distribution system layouts explained. Now at this point, underground cables transist on an overhead three-phase main trunk. The main trunk is routed. Now you remember overhead is, these are the lines that are normally used poles, and underground are the ones that normally run below the ground. Okay, around the feeder service territory and may be connected to other feeders through the normal open tie points. So the underground main trunk are possible, even common in urban areas, but cost much more than overhead construction. So lateral taps off of the main trunk are used to cover most of the feeder services territory. These taps are typically single phase, but may also be two-phase or three-phase. You normally see them in our connections. The laterals are very directly connected to main trunks, but are more commonly protected by the protective devices such as fuses, enclosures, and automatic sectionalizers. Overhead laterals use pole-mounted distribution transformers, or service customers, and underground laterals use mounted transformers and feeders. Now the feeders routes must pass near every customer. We normally say that, and then to accomplish this, each substation uses multiple feeders to cover an allocated service territory. All illustrative feeders showing different types of laterals and devices are shown in the figure. So you can see this figure, look closely onto it. This is a figure showing the feeders and how the power is being distributed. So you can see this is a substation bus, feeder circuit breaker, and then we have the phase 1 overload lateral, phase 3 three-phase radial tap. This is now a substation that is supplying to different loads or different consumers. This one is another one that is a residential load. This is a fixed a capacitor, that is a pole mounted transformer is there, and another one is there for the normal open switch. Now this is called an elbow disconnect for underground lateral. So you can see how the connection takes place. That's connection to another feeder is there. So the primary distribution feeder allowing major components and characteristics. The simplest primary distribution system consists of the independent feeders with each customer connected at a single feeder. Now, since there are no feeder interconnections, a fault will interrupt all the downstream consumers until it is repaired. That is the major problem with that. So in configuration, it is called a radio system, and it is common for low density rural areas where more complex systems are cost prohibitive. So this type of topology or this type of distribution is normally used in the rural areas because of the interconnection problems. A slightly more common configuration connects two feeders together at their endpoints with a normally open tie switch. This primary loop increases reliability by allowing customers downstream of a fault to receive power by the opening upstream switch. So the closing of this tie switch, the only customers that cannot restore are those in the switchable section where the fault occurred. So that is now another characteristics of that distribution. So many distribution systems have multiple tie switches between multiple feeders. Reliability benefits are similar to primary loop with greater switching flexibility. So these highly interconnected primary distribution systems are referred to as radially open networks, or they're radial. Now, primary selective services. Now, certain classes of consumers require high reliability than the single feeder can provide. So the primary selective services connect each customer to the preferred feeder and an alternate feeder. If the preferred feeder becomes de-energized, that is the transfer switch disconnects and preferred feeder and connects the alternate feeder. So they are customers, they're called primary customers. These are customers who should not be in a blackout. They're normally the customers who are given priority. Then we have secondary selective service achieves similar results by using switches on secondary voltages rather than primary voltages. So with secondary selective services, each distribution transformer must be able to supply the entire load for maximum reliability. Other types of networks are called spot networks. They are used for customers with the highest reliability requirements. That is, this configuration connects two or more transformers, that is, feed from at least two feeders in parallel to energize the secondary bus. To prevent reverse power flow through the transformers, special network protectors with sensitive reverse power relays are used. So the spot networks allow multiple components failures to occur without any noticeable impact to customers. So these are high reliable customers. Now places like hospitals, which normally need constant power supply, like industries, maybe industries that process now things that are very perishable, when they even take some minutes without the power. They are common. They are common in central because business districts and high density areas and are big applied frequency outlying areas of large commercial services where multiple supply feeders can be made available. So some typical primary distribution system configuration are shown in the next figure. You can now see that figure. Now we have a substation bus, primary selective. You can see they're the first one to tap power. Then we come to the secondary selective, then the stop network. And then the primary loop is there and the radial is there. The radial is the last because it's the most interrupted one. And this one now goes to the rural areas. Secondary distribution system. A low voltage network or secondary network is part of the electric power distribution, which carries electric energy from the distribution transformer to electric meters of end customers. Secondary networks are operated at low voltage levels, which is typically equal to the main voltage of electric appliances. So most modern secondary networks are operated at AC rated voltage of 100 to 120 volts. Operating voltages require a number of phases, that is the three-phase, single phase, and require reliable dictate the topology and configuration of the network. Electrical power distribution systems are designed to serve their customers with reliable and highly quality power. So the most common distribution system consists of the simple radio circuits, that is the feeders, that can be overhead, underground, or a combination. From the distribution substation, feeders carry the power to the end consumers, forming the medium voltage or primary network. So you can see now a transformer is there that is used to step down. That is a picture of a distribution transformer. Typically in the rural primary feeder supplies up to 50 distribution transformers spread over the wide region, but the figure significantly varies depending on their configuration. So they are sited on the pole tops, cellars, or designated small lots. Now you can see now a typical example of that. From these transformers, low voltage or secondary transformer branches of the customer connections. You can now see the distribution. Now a distribution transformer is there, the secondary main is there, and then the service drop, the primary phase, the primary neutral conductor. So from the transformer, you can see after the transformer has stepped down, now it can take power to the secondary main. Maybe this one needs a three phase, that's why it gets this, and this one needs a single phase, so it just taps the primary phase and the neutral conductor. So the surface drop or primary right surface drop, secondary main left. And now the customers are connected to distribution systems via the service drops. You can see the service drop, normally mostly called in the field as the service cable. Now customers close to the distribution transformers are able to have service drops directly connected to transformer secondary connections. Other customers are reached by routing a secondary main or service drop connection. The two types of service connections are known as in the figure. You can see that figure. Now, systems utilizing secondary mains are characterized by small number of large distribution transformers rather than the large number of small transformers. Now, this can be cost effective for areas with low load density and or large or lot size. So, but increases ohmic losses and results in higher voltage drops. So, increased line exposure tends to reduce reliability, while fewer transformers tend to increase reliability. Now, many underground systems can not service drops directly to distribution transformers and do not use secondary mains. So this focuses distribution transformers to be located within the several hundreds of feet of the customers, but eliminates the reliability concerns associated with the T-splice that are required to connect the underground service configuration. Now we talked about the topologies. Now that you can now see a typical layout of the radial low voltage network. Now for the low voltage, you can see the substation, that is the high voltage substation is there, and it is supplying. It gives a three phase to different houses. That is the urban areas, they are getting the three phase. Now for the rural areas, look at what is happening. These are the urban areas that they are getting the three phase. Now for the rural areas, single phase wires are being because the loading and the consumption is very low. In an overload network, service drops are drawn from pole tops to roof connections. So in a cable network, all necessary connections and protection devices are typically placed in pad-mounted cabinets or occasionally manholes. Buried T-joints connections are prone to failures. Power system protection in radio networks is simple to design and implement, since short-circuited currents have only one possible path that needs to be interrupted. So you can see now here major distribution equipment. We have a reclosure controller, voltage regulator controller, switch. These are big switches, switch controller, capacitor bank, and the capacitor bank controller. Spot networks, we had talked about the spot networks, and we said that they are used when increased reliability supply is required. Now, that is how it is distributed, the spot network. Typical layout of the spot network, because this one has less interruption of power. The grid networks consist of the interconnection of grid to circuits, now energized from several primary feeders through distribution transformers at multiple locations. Grid networks are typically featured in downtowns of large cities, with connecting cables laid out in underground conduits along the streets. Numerous cables allow for multiple current paths from every transformer to every load within the grid. As with spot networks, network protectors are used to protect against primary feeder faults and prevent fault current to propagate from the grid to the primary feeder. Individual cable sections may be protected by cable limiters or both end special fuses, providing very fast short circuit protection. So inherent system redundancy generally prevents customers from experiencing the outages. So you can see the grid voltage networks the way it is. All of them are getting now the same power. Okay, we will be going to the next presentation. But before we go to the next presentation, I would want us to go for a discussion. And I've already created the discussion in the group. The discussion is going to take us the next 40 minutes. So I want people to write what they have understood in the discussion. I'll be there discussing with you. It's a requirement that we have to do. So each member, for your attendance to be marked 100%, you will have to participate in all of them, both the conferencing and the discussion. So I'm going to post some questions there, and I want people, anything that you've not understood on this session or from the previous sessions, I want you to post the questions there. We are going to have a discussion, and after we have had the discussion, we'll come back here and finish with the 2 slides remaining so that we can finish the session. So the next 40 minutes, we are going to spend them on the discussion platform. Go back to the portal and click on this unit. Then there is a discussion created there and talk there. So I'm giving you 40 minutes unless anybody has a question. So we are going for a discussion. Norman. Yes, Norman.
Tunaenda kwa portal ama hapa ulikuwa?
Kwa portal. Norman. We are going to the portal. We are going to discuss there.
Na mimi sina portal.
Kwa nini hauna portal? Portal liko kwa kila mtu. Ukienda ZDS, uko na Zitech email.
Lakini haifanyi.
Kama uko nayo, fungua tu ZDS. There's this thing called ZDS. Enter your email and the password that you are given, and then you just load. Utaziona hapo. Or kama uko na hiyo
yangu haiwezi email ilifail.
So how do you access the classes, Norman?
Ulinifungulia account ya kuingia class na Gmail.
Unaingia na Gmail?
Ya kawaida.
Na kuna app, nataka udownload app ingine hapo inaitwa Module. Use that time to download that app inaitwa Module, and then you enter ZDS at Zitech, and then uingie na hapo utaona sasa hizo units, but in the meantime I want you to now send me again your details, your registration number tena tuone kama tutaconnect Zitech. Sawa. But the rest have to go to the discussion. And last time I thought uliniambia umeingia, na kwani tena ulienda ukangoja mpaka leo?
Details ukaniambia nini iko low network.
Oh, by the way, network ilikuwa low. So the rest wacha waende. I hope Norman pekee ndiye ako na shida. Anybody else with a problem? Okay. Let us proceed. Let us proceed with the next slide. We were still talking on the generation, transmission, distribution of electricity. And then now we are just doing a review of what we did in the morning. You can see there what is electric power system. Electric power system or electric grid is known as a large network of power generation plants which connected to the consumer loads. As it's well known that energy cannot be created nor destroyed, as I had told you, but can only be converted from one form of energy to another form of energy. Electrical energy is a form of energy where we transfer this energy in the form of flow of electron. So electric energy is obtained by converting various forms of energy. We talked about the various forms of energy right there, from solar, wind, gas, oil, and even steam, and so many other forms, even diesel. So, however, it is the invention of generator and had ordered it became a technique to convert some form of energy into mechanical form of energy and other converting it into electrical form of energy using a generator. Generators produce two types of power, that is AC and DC. Nevertheless, 99% of the present power systems use the AC generators. So electric energy has grown immensely over 2 centuries because the flexibility it provides for its use. The variety of use has led this demand to increase monotonously. However, as the load or demand has increased, particularly one requirement is consistent. That is sorry. However, as the load demand has increased, particularly a requirement is that is we must generate the amount required by the load at that very instant, because its large amount cannot be stored or for delivering its high amount of demand. So, therefore, generation of electric energy is happening simultaneously as we use it. We cannot store the energy, so any moment we generate energy, we normally absorb or consume it immediately. Apart from varying demand, the type of current we consume also vary. These variations put many constraints and conditions. This is the reason of the complex and big control rooms areas and the whole power system. So the line network between generation, power station, and consumers can be divided into two parts. We have the transmission system that we had talked about and the distribution system. The distribution system is in between the generation, transmission, and that is distribution, and we can see the transmission and the distribution. Distribution is now giving the power to the load, meaning the consumers of the load. We can explore these systems in more categories such as the primary transmission, secondary transmission, as well as primary distribution and secondary distribution. This shown in the figure below. One line, single line diagram that is typically AC power system scheme. So you can now go down and say we have 5 stages. I asked this question there in the discussion that consider the stages. What are the stages mainly in the power generation. We have the generating station, then we have the primary transmission, secondary transmission, primary distribution, and then finally the secondary distribution. Can see that here. So the power station is here. We are generating the power, and then the primary transmission, that is the overhead transmission, and then we go to the receiving station, which is the secondary transmission, is now stepped down, and then we go to the primary distribution. Primary distribution is the substation here. Now here we have power being distributed to various industries, and then we have the secondary distribution now to various consumers. Now the typical AC electric power supply scheme, you can see a typical AC power supply system scheme or generation distribution. After these 5 levels, the energy must be available as the stated form in terms of voltage, magnitudes, frequency, and consistency. So generation means the conversion of a form of energy into electrical energy. That is what it means. Transmission implies the transportation of energy to a very long distance with very high amount of voltage and magnitude. Moreover, distribution is is fulfilling the demand of the consumers at certified voltage level, and is done in terms of feeders. We talked about feeders. So feeders are small to small chunks of load distributed to different places physically. No, and then we have generating stations that we have already talked about. We say that a place where electric power is produced by the parallel connected three-phase alternators or generators, also called generating station. The ordinary power station plant capacity of generating voltage may be 11 kV or 12 kV where the frequency is 60 Hertz. But economically, it is good to step up the produced voltage from 11 or 11.5 to 132, which we use in our country, or more. In some countries, up to 15,000 kV by step-up transformer per generation. So generation is part of the power system where we convert some form of energy into electrical energy. This is the source of energy in the power system. It keeps running all the time. Generates the power at different voltages and power levels depending upon the type of the station and the generators used. So the maximum number of generators generate the power at voltage level around 11 kV. The increased voltage level leads to the greater size. So presently, the generating stations will employ mainly over the world, following the thermal plant. These are different generating stations that we have, or forms of generation. We have the gas plant, we have the solar plant, nuclear plant, hydropower plant, that is the hydel power, the solar power, the tidal power, the wind power, and etc. There are so many other forms that we can use to generate power. So we generate electric energy through these plants at different voltage levels and different locations, depending upon the type of the plant. They are used for different purposes. That is, we have the base load and the peak load plant. The base load is when the plant is used to handle the base load demand of the system, and the peak load is when the plant is made to handle the peak load demand of the system accordingly. Now, thermal plant, that is the nuclear plant, that is solar plant, wind plant, and the tidal plant are chosen to handle the base load on the system, whereas the gas plant and diesel plants are used to handle the peak loads. Peak loads are those loads. Now, when there's a lot of demand, much demand than the base load, this is mainly governed by the nature of the time they take in the process of starting delivering the power. The base plants take more time in delivering the power, whereas the peak loads must start very fast to supply the demand. Now, like for example, the Africa that we visited there, it is a peak load because it's used to supply the power just at the instant of the demand when the power is really needed. The primary transmission, that is the electric supply, that is of 132 kilovolts, is transmitted to load centers by three-phase, that is three-wire, known as the delta connection overhead transmission. As the voltage level, which is generated at around 11, and the demand is various levels of voltage and at very far away places from the generating station. For example, the generating station can be generating voltage at 11 kilovolts, but the load center is that, apart from that. So therefore, for the delivery of electrical energy at such long distance, an arrangement must be there to make it possible. Hence, the transmission system is essential for the delivery of electrical energy. This is made possible by using the transmission lines of different length. These are overhead transmission lines in most cases. Oh, so we proceed. I'll be giving you these notes so that you go through them. So we have formulas now, calculation, how to calculate these formulas. Now secondary transmission, area far from the city, that is the outskirt, that it gets the secondary transmission, which have connected with the receiving stations. Lines are called the secondary transmissions. Now this is when we get transformers being positioned at different locations. The primary distribution, a substation, and at a substation the level of secondary transmission voltage is 132 and or 66 or 34 kilovolts, reduced to 11 at the step down transformers. So we have all that. We have underground cables and feeders. We have all major control machine to provide substation to make the power delivery. We have the feeders. It is done by the overhead lines, and that then we have for domestic use is further reduced to 110 volts, or for face to face ground, to be used for the individuals of different power factors. So the combined amount of demand and load the entire system, and that must be generated at the instant. But we measure that using a potentiometer. Secondary distribution. Now in this, the electric power is transferred from the primary distribution lines to distribution substation and is known as the secondary distribution. So the substation is located near by domestic consumers areas where the level of voltage reduced by step transformers. So these transformers, called distribution transformers, the three-phase 4-wire, are there. The combined process of power system. Now the entire structure of the power system is consisting of the source, that is generation, the transfer, that is transmission, the distribution, and the load, that is the consumer. The objectives are to rate the voltage and frequency of the loads, reliability of the system so that the power delivery is continuous, flexibility of the system so that the power is available at different voltage levels, and then faster clearance of faults so that it runs well on longer time of life. So we can now see the combined process of the power plant is there. You can see that the generation station, the transmission system or grid, the distribution centers, distribution center 1, center 2, and they're distributing to feeders. We talked about feeders. This one can distribute to several number of feeders, and from the feeders, now power is tapped by the control of the PLC or the SCADA to distribute it to different customers. So those are notes that I'll need you to read on the load varies of the load and light loaded conditions and heavy loaded, the HV and LV. Now we have the typical power system, generation, transmission, and distribution. You can see now this one is combined. Maybe power is generated here using the winds, and then power is sent down to the primary transmission. The primary transmission it is stepped up, and then it goes down to the step up transformer again. It is from the step up transformer, it now gets again to the secondary transmission and distribution, and then it gets to the primary distribution, and then it goes to the houses. So these are the secondary distribution, they are the final feeder elements of a distribution system. It has the feeders, it has distributors, it has service lines and service mains. We had talked about that in the first slide. So elements of the distribution system are there: feeder distribution system. So a feeder, those are electrical power lines which connect a generating station's power stations or substations are called feeders. Remember, the current in feeders in each point is constant, while the level of voltage may be different. So different protection, we have distributors, those tappings that which extract the electrical power supply to the consumers, or the lines from which consumers get direct electric power supply is known as the distributors. Or you can see them. Then the service lines are now the service cables, the service mains. These are the ones, the normal cable which are connected towards the distributors and are consumer load terminals. These are the ones that supply power to the consumers. Now summary, we are summarizing now the electric power system. What are they? We have already talked about them. Then now that is a diagram. Now we have the generation, transmission, and distribution. That is the major power supply system. Then we talked about the separate transformers stepping up for the transmission. After it has been transmitted, it is now stepped down to transmission line, and then finally to the distribution system where power is distributed to different houses. So that is again another diagram of the generation. Now the primary substation, transmission, secondary transmission, primary distribution, and the secondary distribution. You can see all these are transformers. This is a step-up transformer. This is a step-down transformer. Step-down transformer is stepped it down more. And then we have the pole-mounted substations are there. And up to that point, I've finished the slides. So I would like to hear any questions. Anybody with a question before we wind up? We are done with that part of the presentation. I would like to hear questions from you. Other notes have already been posted to your portal. You'll be able to know that. And then this will be part of your assignment, transferring AC to DC electric power. Now, after power has been generated, how now do we transfer or change it? Can you unmute your mic so that I can hear people talk? Alex, Gachoki, Kimberly, you are on listen only. Can I hear people talk? Can I hear people ask questions? I want to hear people talk before we can end the class.